Hello everyone, my name is Tushar Budhwani and I'm here to present our project on generative 3D reconstruction. Our primary goal was to generate 3D models from high-resolution 2D images. We aimed to fine-tune and optimize our approach to improve evaluation scores such as FID and NFS compared to the baseline model. The motivation behind this project was to overcome current limitations in 3D content generation, enabling more creators to incorporate 3D elements into their work without the steep learning curve. To achieve our goals, we successfully completed several key tasks. We created image depth maps necessary for model training and evaluations. We ensured our architecture was compatible with all environments. We optimized encoder and decoder layers for fine-tuning. We implemented attention caching to speed up evaluations. We built upon recent advances in generative models, particularly GANs, which have significantly impacted 3D modeling and reconstruction. For instance, the first research paper demonstrated the capability of GANs in medical imaging to generate lifelike images for better diagnosis. Similarly, Angerman's work on unsupervised depth estimation and the technique demonstrated in the third research paper for creating intricate scenes using locally conditioned radiance fields informed our approach. We used the iNaturalist dataset, which contains 859,000 images from over 5,000 species of plants and animals captured in various situations with different camera types and image quality. The high resolution images in the dataset allowed us to render realistic 3D models after fine tuning.
So now let's discuss about the architecture of the model. We use a backbone which consists of a triplane generator. We also use a diffusion model clip used for generation of the RGB images. We use these generated images for our model, which completes the final RGB images, and they are generating a 3D triplane. The 3D scene reconstruction, we use a triplane. We use the same triplane generator that takes the encoded features from VGG16 and the embeddings from clip and constructs a 3D triplane that represents different aspects of a scene: color, depth, and semantics. We also incorporate a perpetual similarity distance during our training that is between the predicted image and the ground truth image to give better quality in our outputs. In multi-resolution sampling is a strategy where we perform for our training, and it is usually random, or sometimes it can be with a metric. This basically enhances the details and quality of the textures in the generated 3D scenes. So our model uses an existing EG3D model for rendering the 3D models. The authors of this paper actually extended that model to include depth estimation, which is crucial for realistic rendering. Why we do this? Because experiments done by the authors prove that during that using depth is necessary to get to good geometry and quality. So basically, we control the geometry of the generated images using the depth within the render model. Using those depth maps, we are ensuring that the models are visually pleasing and geometrically accurate. Okay, now we go a little bit deep into the model architecture. The architecture is primarily consisting of the backbone triplane 3D model, a generator model, and we take the input. This input starts basically with the positional embedding, the ground truth image, and the ground truth depth map. This goes through a convolution layer and to the encoder layer with multiple convolutions, with increasing the resolution as we go forward. Then there is a middle layer, and then finally a decoder layer. To give a better understanding what happens inside this encoder and decoder layer, this architecture can be further explained in this part of the diagram. So we have in every layer of a encoder, middle layer, or a decoder with a modified resonance block. So this modified resonance block is basically including a time embedding that is necessary to generate 3D model. We have two resonate blocks, and then it goes through a tension layer that is common for forming relations between the points in the images, then a layer normalization, and then a skip connection or a residual connection, and then finally a convolution down for an encoder, convolution up for the decoder. From this, we also to note this time embedding is fed parallelly to all the layers in the encoder decoder, meaning that they are going to be done for the same time for the model. Then the output goes to a final ResNet block and finally a convolution layer. Now, the output of this convolution layer is a stack of images generated. With these stack of images and the ground truth depth map, along with the rays, the cameras for our neural rendering, we use the EG3DR model that is basically generating the images for us, and we get two outputs basically, the RGB image and the depth map. So now let's talk about the training process of all this model. From these two outputs, we calculate the losses, and the losses are like this. With this output image, we take the loss between the ground truth image by using the clip loss. Similarly, we use the perpetual loss on the depth on the RGB and the depth map. An RGB loss is directly on the RGB input and the ground truth image. A depth loss is between the ground truth depth map and the predicted depth map. And a TV loss is basically for the depth maps. It's used as a regularization for geometry supervision for the training. So as I explained, we use clip loss and perpetual loss, and these are quite important because the clip basically uses, it's a pre-trained model and it excels at understanding images, and it can be effective in ensuring semantic consistency between the images and the models and the output of the models. Using clip, we guide the generation model, ensuring the outputs are semantically consistent. And this is particularly useful when the image generation process is conditioned on images or text. In scenarios involving novel views synthesis, clip can also maintain the integrity of the object's identity from different perspectives, ensuring the semantics remain consistent across various views. For the perpetual loss, as mentioned earlier, it's a VGG16 model, and it is known for its simplicity and effectiveness in image recognition tasks. But in our case, it is effective for the similarity distance as close as possible between the predicted image and the ground truth image. And specifically during our training, the images are chosen randomly between the mechanical and normal views. This is proven to be a faster way to learn to learn and generate images. This increases the probability of sampling. By increasing the probability of sampling from the novel views during training, there's one more important note for the training purpose. The images are chosen randomly between a canonical view and a novel view during the training. In this way, the network quickly learns the easier task of image reconstruction, and this increases the probability of sampling of the novel views during training. This probability of sampling is never higher than the sampling of the canonical view. Finally, we come to the implementation of our model set. As explained before, we are using the ImageNet the pre-trained model that was tuned on ImageNet, and now we are fine-tuning on our iNet serverless dataset. For our purposes, we took 1,000 training images and we ran it for 100 epochs, and we are also evaluating for 400 images. So our fine-tuning and optimization. So for fine-tuning, since we have a pre-trained model, we are basically freezing the encoder layer, the convolution layer, and we only have the trainable middle layer and the decoder layer. For evaluations, we are using the same evaluation metrics done by the authors of these papers, the FID, the IS, and the NFS scores. We have also modified the loss functions. Basically, we have that analysis we will show later, but we are using L1 smooth loss for our depth and RGB, as well as cosine for clip. And as mentioned earlier, the EG3D model is a modified one that uses depth importance. The authors used a random way to sample the depths to generate the model. And since we are fine-tuning, we did a slight adjustment and made it to not pick it random, but instead use sorting, which improves the process a little bit by getting quality images. Okay, so here we explain why we are doing the cosine similarity. So this is a sample image I have taken for our comparison. So the top image is a static image, and the second one is like a generated image you can consider. Basically, this is a molecular depth estimation that is used for the depth maps generation for our model training. We use the same images, same concepts here. With these two images, we basically calculate the depth maps using disparity. Disparity is nothing but the distance between the pixel locations between the two images for the same point. By using different similarities, we generate the outputs and we measure which one works the best. So as you can see, the L1 similarity gives a little bit of wrong values, like it goes to infinite depth at these points. Similarly, for the L2 loss, it's slightly better, but not there yet. And finally, with the cosine similarity, it gives the best representation of the depth. So our intuition is that if we use a cosine similarity and we feed it to our perpetual loss using CLIP, this will be a better metric to generate to encode and generate images, because as we can see, the cosine similarity and the cosine loss respectively will give us better results.
Coming to the experiment section, so we have primarily focused on tweaking our loss functions to see how they affect the learning dynamics and computational efficiency. So first of all, our preliminary analysis showed some really good trends with the different loss functions. We noted that using cosine similarity gave the most significant results by decreasing in clip loss, suggesting that the model was effectively capturing and utilizing more relevant information during training. So this is a promising development because it indicates a more efficient learning process. While the original model used an L1 loss, and we also experimented with L2 and L1 smooth losses and observed better performance and also reductions in computation time. This is crucial as it means we can train our models faster and more effectively, saving resources without sacrificing quality. So coming to the experiment section, to like we tried fine tuning here, and we adopted a more tailored approach by updating the loss functions and integrating importance of depth sorting. The results were quite clear. Optimized fine tuning consistently outperformed the baseline across all metrics, indicating that our training regimen was more effective. Especially noteworthy was the performance in total variational denoising or TV loss, which was significantly lower. This implies that the depth images produced are now of higher quality with less noise, which is really important for practical applications of our models. So in the evaluation section, we focused on metrics like FID, fractured inception distance, and inception score or IS. Interestingly, the optimized fine tuning didn't lower the FID scores as expected, which tells us there's a limit to how much the image quality can be enhanced using these methods alone. However, the inception score showed slight improvements, suggesting that image quality did see marginal gains. Moreover, NFS or a non-flatness score was significantly higher, validating the robustness and innovativeness of our model when generating new images. In conclusion, our experiments demonstrated that targeted optimizations in training processes gave better improvements in model performance and efficiency. Going to the next slide, and this is like a tabular format of our FID, IS, and NFS matrix. We got like better results when we tested on like individual species because we used like less number of images per species. However, it gives a good insight that certain generated images gives better results with optimized fine tuning. Okay, coming to the 3D output that our model has generated. So this is the first video of how pre-trained model has generated the output, and this is how the fine-tuned model had generated the output for us. And the last one is the optimized model of ours, where we tweaked with the loss functions, and this is how the video has been generated.